Hello, this lecture discusses sensor placement methods for aerospace structural finite element models. We'll talk about some of the algorithms that are typically used and specifically focusing on the effective independence algorithm. First, a little example to motivate this. Imagine that we were trying to place sensors for a test where we wanted to capture these three modes of the space launch system from this little simplified model. So there are two important aspects to that. We'd need to place sensors so that we could detect the motion, and we'd also want to distinguish the modes. So first of all, detection. Where would we put sensors? Well, to detect the motion, we need a place that's moving in each mode. So for example, for this mode, in this region, it's not really moving. There's like a node there, right? But up at the very top of the launch abort system, there's a lot of motion. So that'd be a great place to detect mode 1 here. Also down here on the bottom of the booster rockets, if that point was inaccessible. Similarly, for this second mode, if we had a sensor on the top, we'd also catch that mode. But notice when we get to this mode, it's spinning about that point. There's not really any lateral motion at the top. So if we wanted to detect this mode, we'd need probably a sensor down here on the booster rockets in this out of plane direction. So with one sensor on the top and one sensor on one of these booster rockets, we could detect all three of these modes. What if we want to distinguish them? Well, these two modes look pretty indistinguishable if all we do is measure on the top, right? We'd also need another sensor, so we have to look for a place that the two modes are different where we could place a second sensor. So we can see here that the core of the rocket and the core stage and the boosters move together in this mode, and they move different in this one. So if we added a sensor here and a sensor on one of the boosters, we'd be able to tell those two apart, right? And then down here, getting to this mode, we'd also probably want a sensor on the other booster so we could tell whether the boosters are moving in phase or out of phase, as we see there. And that would probably be just barely enough to detect and distinguish the modes. The last thing that we might want to do would be to add some other sensors so we could detect the rotation here versus bending there. And we could put a few on. So you can see how for a structure like this, it's not too complicated to figure out where we would place sensors. But this becomes way more difficult as the structure becomes more complicated. This slide is from a presentation given by some engineers from Cordis who were discussing what the work they had done for testing sensor placement to prepare for the testing and then testing of the James Webb Space Telescope. And you can imagine this structure is pretty complicated, and if you have many modes that you're interested in, they boiled it down to about 23 different modes. It just becomes really difficult to look at it and figure out where you would put sensors and to be confident that you've placed them so you can detect everything you might be interested in. So I'll show you a little bit more from that example towards the end here. So next we'll go through a derivation of some of these methods. We'll talk about some basic methods and some more advanced techniques, and end with a few examples. So first of all, a motivating example. Suppose we have a finite element model like you saw there with the James Webb Space Telescope that has about 10 million degrees of freedom. That's a kind of a typical size model, not considered huge. That space telescope actually had about 1 million or 2 million. Now you could probably cut that number down just by throwing away a lot of points where you know you can't measure. Say you have nodes on the interior of a structure where you can't get to. Things like that, places that you just can't attach anything, you're not allowed to touch. So say we can take that 10 million degrees of freedom down to only 1 million. And we want to do a test with 600 sensors, which incidentally is the number of sensors that's being used on the Space Launch System tests that are being planned. So given we have 1 million possible locations and we want to pick the 600 best ones. So if we think about the number of possibilities that we have to test and look at, there's 1 million possibilities for the first sensor, 1 million minus 1 for the second sensor, down to 1 million minus 599 for the last one. Or, roughly speaking, this is 1 million to the 600th power possibilities for all of those, for all of the sensor locations. So that's a huge number. Now, actually, this was about as far as I could get on it, just throwing this idea together myself, but I happened to be great helping my daughter with her math homework, and remembered that actually the formula, if order is unimportant, is the n times a combination NCR here. So there's actually a formula where it's 1 million factorial over 600 factorial times 1 million minus 600 factorial. So these two terms are this right here, but we had to divide by 600 factorial to actually figure out what the real number of possibilities is. Anyway, as you I got curious, so I tried to do this in MATLAB, and I found that it's impossible to take 1 million factorial in MATLAB. The number is too big. Incidentally, about the biggest number that MATLAB can store is 1e to the 300, which is about 171 factorial. So that wasn't going to work, but I did find a little algorithm that could give you the log of a factorial. So I could calculate the log of 1 million to the 600th power. Actually, that we can just do by hand. That's just 10 to the 3600 or 3600. And the algorithm could give me the log of 600. And if you subtract those two, you get 2192. So there's only 10 to the 2192 possibilities. Just to put that number into perspective, if we had an algorithm that took 1,000th of a second, so we could test 1,000 possibilities every second. In a year, we could only test 10 to the 10th possibilities. So these numbers are just impossibly large. There's no way you can just brute force explore all the combinations, all the possibilities. And even if we use the modal kinetic energy algorithm that we talked earlier to say take our 1 million possible sensor locations down to 5,000 that we think are, the best. Even there are 10 to the 765 is what I calculated, or just a huge number of possibilities. So we're not going to be able to solve this problem by brute force. We're going to need some algorithms, and any algorithm is going to be suboptimal because no algorithm can explore all of those possibilities and guarantee you that it's come up with the best approach. So a couple examples of how this is done in industry. One is the condition number algorithm by Randy Mays at Sandia. And there are actually lots and lots of other algorithms that probably work on a very similar principle. This is just one that I happen to know about. But the basic idea behind this approach is that if we're doing a modal TAM, we want to be able to invert phi sub m, or the mode shape matrix, if we only have the mode shape matrix measured, or if we only measure the rows corresponding to our sensor locations. So the 10 million degree of freedom finite element model, right? This phi would be say 1 million by number of modes. And when we do the test, this becomes phi, this becomes the number of master degrees of freedom by the number of modes, or the number of sensor locations. So we want to be able to invert that matrix. If we can, then we can know uniquely what every mode in the structure is doing. We'll talk more about that later. But anyway, one metric then that you can use to judge the quality of your sensor set is the condition number, which tells us how invertible the matrix is. And this is defined as the ratio of the largest singular value to the smallest one. So basically a small condition number is good here. So the algorithm that Mays uses here is we typically start with a set of sensors. You could even maybe just start with one, but typically you'll start with a few sensors that are placed such that you can visualize what's happening in the structure well. That's probably the most basic starting point, is placing a few sensors around so you'll be able to see how the structure moves. And then from the pool of remaining candidate sensors, we add one of those to the set and we check the metric, or we check the condition number. And then we figure out which of those 5,000 sensors gave us the biggest improvement in the metric. So lowered the condition number the most in the case of this algorithm, and we keep that sensor. And then we just repeat and we add another sensor and another sensor till we get to the number that we want. So here, the number of calculations you have to do, if you have 5,000 candidates, you still have to check this metric 5,000 times, but then you do that 5,000 times at most 600 sensors. And so it's a reasonable number. You can do a calculation like this in, minutes on a computer. So a lot of other algorithms use this same concept with just a different metric. Here, we're doing it based on the condition number. Some other possible metrics are the maximum off-diagonal in the orthogonality matrix, because we've talked about the fact that the Air Force and NASA put requirements on how big those numbers need to be. These off-diagonals need to be less than 10% typically. And so sensors are placed to try to satisfy that metric. In other industries that aren't aerospace, maybe the Mach matrix off-diagonals are used instead, as they're a measure of the independence of the different modes. We could also look at the accuracy of the TAM frequencies and shapes, and there are lots and lots of other metrics. So anyway, those algorithms would use the exact same approach, but just using a different metric. Let's shift gears, though, and talk about effective independence, which was developed by Kammer, a former professor at UW-Madison in the 1990s. This algorithm, he took what we talked about above with the condition number algorithm, independence of the modes, but he also considered signal strength, or how large will the vibration signal be at each sensor relative to noise. Similar to what we talked about earlier in the beginning. And this is important because a typical structure, won't just be uniform. The satellite example we've talked about in class is kind of a beam, but it has this core where you have a lot of mass, right? And so this is important because it has a lot of mass, but it's going to have not much motion. It's going to be hard to measure there, so signal strength will be a concern. So we really have to think about both of these things. So one of the foundations of the effective independence method is this idea that our response is a superposition of the mode shapes and the modal amplitudes, but it will be contaminated by noise. So the noise, if we use some statistics to understand this, here E of V is the expected value. So the expected value of noise is 0. We imagine that if we average enough times, or if we take enough measurements, that they'll all be clustered around the true value. So noise is typically 0 mean. And here's a formula that you all know. The average is just the sum of the terms divided by the number of terms, right? The other important quantity is the standard deviation. Here's a formula that you may or may not remember for calculating standard deviation. But you can actually show that if the signal is 0 mean, the standard deviation is just the expected value of the signal squared. So that's used to define a covariance matrix, which is the expected value of V times V transpose. So for example, if we had 2 sensor locations, 2 points, we'd have V1 and V2. Then this expected value, here we're calculating the product V1, V2 times V1, V2 transpose. And so that's what gives us this matrix right here. And if we calculate the expected value, we'd see that the diagonals are 0 if the 2 variables are independent, if the noise isn't tied in some way, which is often an assumption we make. And then on the diagonal, we would get the standard deviation squared of each of the sensor points. So the short version of this is that this expected value gives us R, a covariance matrix, which is a measure of the noise that we have. So we'll use that to quantify the noise. And then what about sensor independence? Well, we'll use the same idea we just talked about. Given that U is equal to phi times Q, if we wanted to estimate each of the modes, we would need to invert phi. So we need an invertible matrix or a good condition number. And if we can successfully invert phi, then we can determine U at any point on the structure. We know how the structure is moving. We could compute the stress. We could do a modal acceleration analysis or a modal displacement analysis to compute the response. So we basically know everything that's happening. So those are our 2 metrics. So effective independence recognizes, though, that when we apply this to estimate the modal displacements, we're applying that to a noisy measurement U. So our estimate of Q will actually include the effect of that noise. So if we take the difference between Q and our estimate, that's the error due to the noise. That ends up just being phi inverse V. And so if we want to minimize the noise in the modal coordinate estimates, we can calculate the expected value of this and minimize that. And so that is what defines the matrix Q, Q inverse, that's used in the effective independence algorithm. So you can see the math steps here. We plug in here phi inverse V, and then we have phi inverse V transpose, and then using this rule of the transpose, we flip the order and transpose both terms. Anyway, this Q ends up depending on the noise in the sensors, but also on the mode shape matrix and its inverse. It has to be invertible. So this one matrix captures everything, and all we have to do is try to minimize Q inverse to minimize the noise, or we try to maximize Q, and that will give us the smallest noise possible. So that's the foundation for the modal effective, or for the effective independence algorithm. A couple other details in the derivation. Typically, we don't know the relative noise characteristics of the sensors. That's not entirely true. There are cases actually where we do know something about that. But a good starting point is just assuming that all the sensors have the same noise. For SLS, incidentally, there are various different kinds of sensors being used in different places, and so you could actually improve on this and account for that. But anyway, we can start with that. And then what we do is if we were to do an eigenvalue decomposition on Q and find a set of shapes that will diagonalize the Q matrix, we get those shapes psi, and then we can put Q in a diagonal form. If we do that, then the eigenvalues tell us how Q gets its strength, or where all of the strength is found, what shapes it's found in. And so if we want to maximize Q, we would want to maximize lambda, or we want to keep all of the eigenvalues that are large and discard the ones that are small. So the last further detail is that the diagonalized version of Q, we can plug in Q as phi transpose R phi, and basically we end up with two vectors that are transposed and multiplied together to give us each eigenvalue. And each of those vectors has a length of the number of sensors. So these vectors here, A, their length is the number of sensors. And so you can see that like each term, all right, well, let's just look at a simple example. So say we had A1, A2, transpose A1, A2. This would just be A1 squared plus A2 squared. So if we want to maximize the product, we can see how each sensor contributes to that sum. And so we can keep the sensors that have large values, large contributions. They're all positive contributions, and we can throw out sensors that are near zero. So this finally leads to the effective independence metric, this variable ID, which is that vector that we defined above. Actually, it's a matrix, and each column corresponds to one of the modes. So each vector is a single mode. So we take that matrix, we square it. This is MATLAB notation for squaring each value. And then we normalize it by lambda inverse. And what that does is that kind of treats each column similarly, or basically treats each mode as if it has equal importance. And if for some reason you knew that one mode was more important than others, you could put some other weighting in there, but typically that's what we would do. So anyway, this is a matrix that's the number of sensors by the number of target modes. And if you just want to know the importance of each sensor over all of the target modes, we take the sum along each row, and this then gives us a vector. This is just a number of sensors by one vector that tells us the effective independence, or the value of each sensor. And that's the basic idea of the algorithm, or that's the metric that the algorithm is based on. So once you know the importance of each sensor, you could go a few different ways. You could keep the sensors that have the most independence, or you could throw out the sensors that have the least independence. And what's most typically done is the second, where you would throw out sensors that have the least independence. So here are the Commer's notes that you have a PDF on the course website. One example is a system that has these two modes. So you can see that there's something unique about this sensor location, because it's the only place where you can tell those two modes apart. And if you calculate the effective independence, you get these numbers. And so it would tell you that if you have to only keep one sensor, you eliminate the points that are less independent, and you would keep only that sensor. So again, this is a simple example. You could do that just looking at it, but for more complicated systems, this can be really valuable. So let's look at how this works on this space station model that we've looked at a few times. And suppose that the first 7 elastic modes are our target modes, and you've seen those in your homework. Here's one of them, just so you remember. So you have 7 different modes like that we're interested in and that we're going to want to place sensors for. So with effective independence, we have that metric, so it's just multiply some matrices, do some linear algebra, a couple lines of MATLAB code, and out comes this effective independence. This is that EFI that we defined in the notes. And so this tells you the importance of each one of these sensors. These are really important sensors. These are the least important sensors. And you can then proceed to place sensors. So what you would do is you would throw out these two, since they're the least important. And it's interesting, those are the two points where the concentrated mass is, the core of the satellite is. It's thrown those out as it's considered both the signal strength and the motion and the independence of each point. It's interesting to see how this evolves. So, sorry, these plots are old, so there's no colors, but that curve we were just looking at is this bottom curve, and that's the first iteration. And it says you would throw out one, or let's say we throw out the 2 worst sensors in that iteration. For the next iteration, we'd get this curve right here. So that's iteration 2. Then we would throw out the 2 worst sensors in that iteration. And then we recalculate effective independence again. So for iteration 3, we'd then throw out these ones. And anyway, by the time you get near the top, you have a sensor set. And it's a balance between capturing the points that are needed to preserve the independence of the modes and the signal strength. So we didn't take the points right on the core of the satellite where all the mass was, but we did take some points nearby so we could tell what's happening there. So these points are nearby, so they have better signal strength, but they also kind of capture the motion near the satellite core. So there's an example of effective independence. And there are some other examples here. This is something Kammer worked on in the 90s, I believe it was, looking to place sensors on the space station on orbit. So in this case, each sensor was going to cost them something like $1 million by the time you did all of the qualification, you launch it, you mount it, use the astronauts' time to install it, connect it to a data acquisition, all of that. So hugely expensive and important to not waste any sensors. And it's complicated, right? You have these solar arrays, you have some flexible parts, some stiff parts, some massive parts. It's not trivial just to look at this and figure out where would be a good place to place sensors. Their goal in this case was to measure all of these modes of the space station. And so Kammer did a study where he looked at effective independence versus just the kinetic energy method that we talked about earlier. and using these to rank and to reduce a candidate set down from 187 down to 70 sensors. And this is what he was able to come up with. And these are the final set of sensor locations that he came up with, assuming that they could afford 70 sensors. I can't remember if they were actually able to put 70 on or they put fewer on. I know there are at least tens of sensors up there at this point. So anyway, that's an application. I can show you one other. This is actually a paper that Kammer and I wrote several years ago. Elizabeth Bergman was a grad student here. And we were looking at different sensor placement algorithms and things. And so here we used a simplified, unclassified satellite model. And so you can imagine these are really flexible solar arrays. We've got some a little bit less flexible antennas, reflectors here. They're on a flexible connection, and then a fairly stiff and massive satellite core. And so, applying the algorithms here, this is what the effective independence algorithm gave us in this example. And this is one of the complaints about the algorithm, is it does tend to kind of cluster things around the edges because of that, because it's focusing on signal strength. Some of the later papers that I've seen use actually mass-weighted effective independence. So they take Kammer's effective independence and they use the mass matrix to weight the mode shapes. And then they calculate the effective independence, and some people find that works a little better. Oh, and by the way, this is the condition number algorithm. So we started with a set that included this, nice grid of points. And then effective independence came in and told us what other points might we want to measure on that we didn't think of. Or sorry, not effective independence. This was the condition number algorithm. And it basically came up with all of these points. And some of them were actually helpful. But again, the clustering of points on the core doesn't really seem like a good thing. Seems like something funny might be going on there, just an imperfection in the algorithm. But anyway, there's the case study. Finally, this is the Cordis study that I talked about, the finite element model that we saw earlier. This is what they finally came up with for their accelerometer set. And there's so many, it's a cloud of sensors. So it's hard to say too much about that just looking at it, but they were successful in this case at capturing all of the motions that they were interested in. So so those are some examples, some studies. Just a few thoughts to wrap up. All of these algorithms are based on a metric that tries to measure how good a sensor set is so that we can iterate on that metric and then come up with an optimal set. The problem is we can't come up with a perfect metric that really includes everything and weights it in the perfect way. And as a result, no sensor placement method can really be perfect. We've focused on detecting the modes and distinguishing the modes in this lecture. But there are really a lot of other things we might think about. The orthogonality and cross-orthogonality of the TAM. That does have to do with the distinguishability of the modes, but it can vary depending on what kind of TAM we're using. And we don't even really know what's the best TAM to use for a particular problem. We haven't talked yet about the fact that we want a sensor set that's robust to changes in the finite element model too. Right. We don't just want to be accurate for the current finite element model. We want to be accurate for the finite element model after we've fixed it to correlate with the measurements. Okay, and then all of these things. Oh, and we want each sensor to contribute something new. We want it to be important. But we also want a little bit of redundancy because there are always a few accelerometers that will fail during the test. And that can be a problem. One last thing that I'll mention is if you look at a commercial software, so IMAT is made by ATA Engineering. They do this kind of work day in, day out. So some of the world's experts on testing, finite element model updating, sensor placement. And so it's interesting, you can go to their website and you can read about what they do. They use a genetic algorithm for accelerometer placement. And you can actually look at a demo that they do. In their case, they're demonstrating this on a truck, and they actually make this even more complicated than what we've talked about. They say that we're interested in one set of sensors that will work for two tests, one where the truck's carrying a load and one where it's all by itself. So already they've thrown a little bit of complexity in there. And then they used an algorithm called iterative residual kinetic energy to get a starting set of 500 DOF. And then they used their genetic algorithm to boil that down to a smaller set of ideal DOF. So anyway, you can go look this up and see how this works. But in the end, they're able to come up with a set of sensors that works for the truck with and without the container using this approach. So that'll give you an idea of the kind of approach that's used. It's using some of the tools that we've talked about and not using others of them. Incidentally, so ATA was using the iterative residual kinetic energy algorithm. If you go and look up the paper where they actually first presented the IRKE method, in the end, they actually find that mass-weighted effective independence did a little better job than IRKE at reducing a sensor set down from a candidate set to an optimal set. So actually, in this case, reducing it down would be going that way, but it was mass-weighted effective independence was usually just a little bit better, but they were similar. So again, there's some art to this. It's not finalized, but effective independence is a well-known and effective tool, so it's a good thing to learn about and give you a sense for what these methods do. So that concludes this lecture. Thank you for listening.